So, hi, my name is Hermann Kroll, and today I present you our paper, A Toolbox for the Nearly Unsupervised Construction of Digital Library Knowledge Graphs. This is a joint work with Jan Pörkelbauer and Wolf Thilo Balke. The toolbox is available at GitHub. It is shared as open source software written in Python and published with a free license. The main objective of our toolbox is to take natural language texts and to transform them into a structured representation. Therefore, the toolbox aims to bypass the need for training data almost completely. I will go through the main components of the toolbox step by step. So we have entity linking, information extraction, and cleaning. Let me start with entity linking. So to do entity linking, we design an own dictionary-based entity linker. It is very fast and reliable, and it produces links between a text and a pre-known entity vocabulary. Of course, the linker does only a dictionary-based lookup, so it might not be as precise as domain-specific entity linking with additional training data can be. So if you need the maximum and precision, then it might be beneficial for you to integrate your own domain-specific entity linking tool. And how you can do it, we have, as a demo, we have integrated two biomedical tools to show you how you can do such an integration. Besides entity linking, we support an interface to Stanford Stanza. Stanford Stanza performs named entity recognition by detecting entities such as person, events, dates, locations, and more in the text. So in sum, they can detect up to 18 different entity types. The main problem here is that Stanford Stanza does not deliver unique entity IDs. So maybe one named entity might be Obama, and another named entity might be Barack Obama, and you must later identify that both belong to the same concepts. But therefore, Stanford Stanza does work out of the box, and you can apply it in your domain of interest. Going to the information extraction step, we completely rely on unsupervised information extraction. On the one hand, we support the extraction of statements via open information extraction tools. Therefore, we integrated support for the Stanford Core NLP suite. It's a bit older but very fast and reliable, and to one of the latest neural open information extraction tools, OpenIE6. It's more precise but very cost intensive because you need a good GPU to perform the extractions. In general, open information extraction yield many statements, and we only care about statements which talk or which involve domain-specific entities. And so our toolbox supports a filter to automatically remove all statements that does not talk about previously detected entities. So you can activate or deactivate this filter to clean the open information extraction output. Because open information extraction is known to be very precision-oriented, we implement an own recall-oriented technique, which we call PathIE. The main idea of PathIE is that we perform a path-based extraction. So if two entities are detected in the same sentence, and a verb or keyword appear on the closest grammatical structure between these entities, then we will export this as a statement. So take the verb and keyword as a predicate and the entities as the subjects and objects. That's why PathIE is recall-oriented, but it already requires entity information from the previous step. Open information extraction and PathIE will lead to many synonymous predicates. So in our biomedical example, we might have some statements which have treats as the predicate. Another statement might have aids or prevents as the predicate, and they all describe the same relation, the hidden relation treats. And to unify these different synonymous predicates, we have developed an iterative predicate unification algorithm that maps synonymous predicates to precise relations. The idea is that you perform the extraction step, then you have a database with these statements, and then you get some statistics. So what is the most frequent predicate, and so on. And experts can read these predicates, have a look in the statements, and can then build a relation vocabulary. In this example, they decide to build a relation which is called treats, and add the synonyms aids and prevents to this relation. Then the predicate unification can be applied, and the database will be updated. And now all predicates which are aids or prevents will be mapped to the relation treats. However, there might be more predicates, and it might be very exhausting to define all predicates in this relation vocabulary, and therefore we integrated word embeddings into the process. So a word embedding can be used to give you more information about similar words. So for example, if there's a statement which talks about the predicate cure, and cure does not appear in the relation vocabulary, then the word embedding will be used to find the closest match, in this case maybe treats, and then cure will automatically be mapped to treats as well. This is our algorithm. You can repeat the iteration steps, and you can control the relation vocabulary which is built. In addition to this predicate cleaning, we also support the cleaning by type integrity constraints. So domain expert might define that the treats relation should only be a relation between drug and diseases, and if the filter is applied, so the integrity constraint is checked, then all statements which does not match this signature will be removed from the database. We have performed several evaluations to understand how well our tools perform, and in sum, we can say that our toolbox achieves a moderate extraction quality. So if you are interested in more details, then please have a look in our paper. There you will find several tables which show you how much precision or recall can you expect for your concrete application. And now let me come to a conclusion. We know that supervised entity linking and information extraction outperform our toolbox. So if you have training data, then this will be better than using our toolbox. But training data require a cost-intensive acquisition, and this might be very exhausting and very cost-intensive in a domain and might hinder the construction of a knowledge graph in practice. And precisely here we propose our toolbox that bypasses the need of training data in the extraction phase completely, but requires two vocabularies, an entity vocabulary and a relation vocabulary. And thus, the toolbox can enable workflows which are otherwise too cost-intensive to concern. So thank you for your attention. If you have any questions, contact me via mail or on Twitter.